Now we will discuss about curves and functions on a manifold. Let's talk about curves first, and we will start with open curves. An open curve in manifold M, where again the dimension of M, let's say small m, is a map. Let's call that map as C to denote that it's a curve from an open interval a to b to m, such that this condition is satisfied. That means a is less than 0 and 0 is less than b. Here a and b can vary from minus infinity to plus infinity, and we chose them in such a way that 0 lies in between them for our convenience. Here, when we defined this thing, that is the open curve, we assumed that the curve doesn't intersect with itself. And if our curve, so assumption is the curve doesn't intersect with itself. Okay, moving on. If our curve or let's say if the curve that we're dealing with, if the curve is closed, then we think of it as a mapping from the circle S1 to M. That is, if my curve is closed, I can now define another map C from the circle to the manifold. So this is an open curve on the manifold M C. It takes points from, let's say, A to B, where 0 lies in between them, but A and B, they are not included, and it maps those points like that, C. And if the curve is closed like this, you can think of it as taking points from the circle and then mapping it to the manifold itself. So these are the definitions of an open curve and a closed curve. And on an open chart, a curve has coordinate representations. So on an open chart, let's call that open chart as U phi. Obviously these charts are open, but we are still calling it explicitly open chart. A curve, let's call it C of t, where t is some parameter, has coordinates, or coordinate representations in the following manner. Let's call that coordinate x. This is just phi of c from R to Rm, and we use a picture to make this thing clear. So let me draw the picture. Let's say this is the interval where these 2 points are excluded. Let's say this is A, this is B, and this is my manifold M. on that manifold. This is my chart, this is the curve. Let's say this is the point, or any point on the chart. So what C does, C maps the points between A and B to this curve, right? So this is what C does. So this is C. What is phi? By our convention, I think you have guessed it by right now, it's just a local homeomorphism from the manifold to the m dimensional space Rm. This is Rm, and what phi of C does is that it takes this interval into this m dimensional Euclidean space. So what is happening over here actually? Well, first you are taking points on this open interval like this. You define a map from this interval to the manifold, or so to say the open chart to be more precise. Or you can have a curve and then you draw some open chart, open set around it, or open chart around it, whatever you want to call it. And then you use the local homeomorphism to take any point on this curve to assign some coordinates to it. So if you do this for all those points, you'll also have a curve in the m dimensional space. So essentially this coordinate thing is coming from the composition of these maps. Okay, and what phi.c actually does is that it takes R to R of n. Let's say this is acting on the open interval AB. Now this is all we have to say about curves. Now let's talk about functions. The definition of a function on a manifold. A function on a manifold M is a smooth map from M to R on a chart, let's say the U phi chart. The coordinate representation of F is given by F phi inverse 1 that takes you from Rm to R, and this is just a real valued function of m variables, or you can also call it a vector valued function. But since we haven't defined what is a vector yet on a manifold, we don't want to say that. We are just calling it a real valued function of m variables. Okay, so this is nothing but a real valued function of m variables. And the set of such smooth functions we denoted by the calligraphic F over M. Now this definition might confuse you, so let's again draw a picture. Let's say this is my manifold M. This is the local coordinates. You can take any point P, and since we defined a function is something like this, that it takes a point from the manifold and then it maps it to a real number, right? And we are defining it through that function itself with the composition of the inverse of the local homeomorphism. So what is happening essentially is that this phi inverse 1 is mapping a point, let's say x1 x2 dot 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 dot, dot x of m, to this point P, and then this P is getting mapped to the real number, some real number. This is how we define a function on a manifold. And what we have seen so far, this is just a real valued function of m variables. And then after this we will discuss what are vectors and one forms, and those will be more important to us because that will have to do with the differentiation and the integration on a manifold. So from next lecture we'll discuss vector, one forms, and then slowly we'll talk about flows, lead derivatives, and finally we'll talk about integration on manifolds.